Our next presenter who's going to be up is Karthik Subraveti, who will be presenting Backbone Change Management, scaling at 1 million+ changes each year. Karthik is a seasoned software engineer with over 15 years of experience in the networking industry. He currently serves as the tech lead for WAN Management at Meta, and it's a pleasure to have him speaking with us today. Welcome, Karthik.
Hello. Good morning, everyone. Thank you for the introduction. I'm Karthik Subraveti. Been with Meta for the last 5 years. And today I would like to be presenting on this topic, Backbone Change Management, scaling at million operations a year. So before we get into the topic of change management, I would like to just talk about what I mean by a change. A change is what we consider any modification to our network infrastructure, which could be like image pushes, configuration changes, routine repair operations on the network. We consider all of them changes on a network. Why is change management in backbone networks hard? Change management is in particular not a new topic. It's been around for years and even decades. And I would think it scales at much higher numbers in the compute and the server domains. But backbone networks are incredibly complex and diverse with several constraints. This is an environment we don't control, and sometimes we cannot even access. It may take days to even weeks to repair some issues on the backbone network. And performing operations in this part of the network is high risk, and the chances of impact is even higher. And at meta scale, we are talking about impacting millions to hundreds of millions of users. To just talk about a bit of the scale which I'm going to be presenting about, like we have over 25 plus data centers, 85 plus POPs, and millions of fiber miles. And on top of it, we have different types of networks for different use cases. They include DC to DC networks, DC to POP, POP networks, management networks which provides out-of-band connectivity to our production networks, and optical networks which underlies the IP networks. All of this scale means that we have thousands to hundreds of thousands of devices for which we have to perform routine operations and repair operations just to keep the network operational. And on top of it, if you have to support our business use case, we have to add capacity on a constant basis. All of this means that our change management has to scale for millions of operations on our network. But this has always not been the case. So I would like to take you through some story time on how things were a few years back. So long ago, operations were less complex, teams were small, and work was easily coordinated. You can imagine it was like a small village where everyone knew everyone, and if you have to make changes on the network, you could just talk to people across the desk and push changes onto the network, and it was done. It was efficient, in fact, like to actually make changes on the network. But soon, networks became more complicated, and the operational complexity also grew. This means that it was no longer a village, it was a city, and it was a city with a lot of regulations. The over-the-desk conversations became war rooms, and all of the manual scheduling means that we have to have a lot of complicated spreadsheets to make this happen. This no longer scale. This means that we have our initial problem statement to build our MVP. The goals of our minimum viable product were threefold. One is that we wanted to build a central place for providing visibility into all operations happening on the backbone network. Second was that we wanted to block risky operations, not just before the start. We wanted to block risky operations at if we deemed that it was risky at any point of time during that operation. And finally, we also wanted to support external vendor maintenances. Before I talk about the MVP, maybe I can just introduce what I mean by an operation. Operation is something which impacts a network entity. It has a fixed start and an end time, and it has a well-defined operation type. This was our MVP, the scheduler. We built a scheduler, which was a central place for storing all operations. It could schedule operations based on a risk determined, and it could automatically trigger shifting traffic away from the network entity and through the network entity before and after the operation. How the scheduler works is that scheduler builds the complete future state of the network. What I mean by future state of the network is that scheduler is aware of all of the operations which are currently active. It is also aware of all of the outages on the network, and it knows what are the operations which we would like to schedule on the network. As shown in the bottom right corner, you can imagine scheduler almost looks at 24 hours worth of time, breaks them into smaller time windows, and it analyzes risk in each of these time windows. If we determine that there is a risk associated with that operation in any of the time windows, then we provide visibility into the risk and we block some operations and we make the other operations runnable. As shown in this image, you can see that we have 3 operations, one in blue, purple, and brown, and we have identified the risk associated with the brown operation and we have blocked them. Scheduler does this with using 3 primary constraints. The first constraint, as shown in the GIF, is the simple deconflicting constraint. Here, when we determine that multiple operations are operating on the same network entity, then we identify that as a risk and we block them accordingly. The next is a more interesting one, which are the scope checks. Scope checks are limits which we can set on the number of operations which can be performed within the device groups. These device groups can be arbitrary set of groups which can be set by the product owners. For example, we could set a limit such as I would not like to perform more than I wouldn't want to impact more than 25% of the DC to DC capacity through because of my operations. I wouldn't want to impact more than 1 peering device in a region at a time. All of these are examples of scope checks. Scope checks are extremely critical to contain the blast radius of operations. What I mean by this is that a new operation would be allowed to make a change on the network not only once the previous operation is complete, but also once the previous operation is complete and we have run health checks to ensure that the operation did not have any adverse impact on the network. And this helps to contain the blast radius on the network. And the next one are the risk checks. Here, we overlay the network failures on top of the network, and we analyze whether we have enough capacity to handle demands on the network. You can imagine something like Google Maps with historical traffic information. And now imagine we have some road maintenances happening, and we want to really verify whether on top of all of these road maintenances, the traffic is going to look red or green. If it looks red, it indicates that there is going to be a congestion on the network and we are going to block some of the operations. If it looks green, we are all good to go. And with this scheduler working and all of the checks we have added, we were able to build the initial version of the product, which could allow anyone to manually schedule operations, and it would block them based on the risk analyzed on the network. However, the story doesn't end here. We want to reconfigure the world. We have always had a perennial problem that we have had a lot of stale devices running on the network. They include stale devices with old configurations and old images. Building a scheduler meant that this was a perfect time to exploit and build something we wanted to always build, which is fully automated fleet-wide operations. To support this, we built another system called the orchestrator. Orchestrator supports 1 device batch per operation. We manage it manages operations across several device batches. And finally, it also supports operational health checks to ensure that operation is complete and it is fully healthy. Now, the orchestrator creates a special type of operation within the scheduler. These are the operations which don't have a fixed start and an end time, but it can be opportunistically scheduled based on the risk. These operations do not have, for example, if you want to perform a fleet-wide upgrade of a network with all of the new images, you don't have a fixed start and an end time when you want to start and complete it. you want it to be done like say 10 to 15 days. In that case, you would schedule them, and these operations would be scheduled by the scheduler when there is low risk on the network. And if it cannot be scheduled, it will just be moved to the next time window whenever it is possible. So with this, we have now been able to build a basic scheduler which can schedule operations and an orchestrator which can support fleet-wide upgrades. But the story is not done yet. We have more incidents on our network, and before I get to it, I also want to provide a little bit of a background on our external vendor maintenances. I briefly mentioned that this is something which we wanted to support on our scheduler. So Meta relies on a lot of external vendors for our fiber capacity. Just like we have operations on our network, they have operations on their network. And when they do have them, they send us across a lot of maintenance notification, which our systems automatically parse and create maintenances on our system. However, we have had several incidents, and probably in particular, we have had a scenario where a region would have almost disconnected because of 3 concurrent fiber maintenances from 3 different providers. However, since we identified the risk too late, it was already like it incurred a lot of trouble for all of our services to move out of the region because of the significant risk detected. This means that we had to build a new system which could provide early warning to our users. So we built the early warning system, which was the Evaluator. The Evaluator was actually like slightly modified version of scheduler, which would run not only for 24 hours, but it could identify risks 2 weeks in advance and de-escalate. For external vendor maintenances, it meant that like we would contact, our partner teams would contact their teams and ask them to reschedule it. For our internal planned operations, it meant that they could identify, they have visibility into how their operations would be scheduled ahead of time, and they could reschedule accordingly. And additionally, we also set up the initial version of operational policies to identify what are the safety checks which must be run in scheduler, and also like the system which shifts the traffic on the network, and in what cases we should escalate. And the previous pattern we have, the story is not done yet. We next have the story of missing operations. The onboarding to scheduler was not instantaneous. All the operations were not are not on scheduler, and there were still large-scale migrations happening, which got delayed by unexpected operations. For example, we had another incident where decom was performed on live circuits. So there were other systems which are built with the awareness of operations on scheduler, and since it did not have visibility into these decom operations, like we ended up accidentally, those circuits ended up coming back live, and decom was accidentally performed on the circuits. This meant that we could not be in this partial scenario where some changes could be on the scheduler and some changes could not be. We had to onboard all of the operations. But the challenges were that scheduler was far from perfect. Scheduler was very noisy. It was blocking a lot of operations, and it needed people to actually take a look at all of these operations and help move them along. And it also was not as fast as what people expect it to be. Obviously, like when people are able to make changes directly onto the network, it's much faster. But even then, like scheduler was much slower than their expectations. The reasons were twofold. Scheduler considered all of the operations to have equal risk. This assumption was inherently not true. For example, when we have people, if you have to compare a case where you upgrade the images across the entire fleet versus there being a planned operation where someone is actually on the field trying to make all of these operations work, the risk profile of these operations are different. In one case, maybe you want to go more conservatively and slow. In the other case, you are okay going a bit faster. So what this means is that like we had to understand the intent of the operation, and we supported the intent-aware scheduling. And in implementation, this translated to like where we could, for planned operation, use relaxed scope checks, while for fleet-wide upgrades, we wanted to implement stricter controls. Similar to the challenges we observed in scheduling, there were other problems with health checks. Initially introduced to smoothen operations, we have had health checks to be performed before the operation is performed, before the operation is complete, and also after the operation is complete. However, the health checks were again noisy. Health checks were not perfect. There were a lot of unrelated health checks failures for some operations, and that caused noise and led to frustration. Additionally, there was also confusion around where to add the health checks, whether is scheduler the good place to add, orchestrator, or should it be added in individual workflows, which led us to evolving the health checks in our system. We added support for workflow-specific health checks. So these were added in addition to the baseline checks. Workflow health checks were added in the orchestrator before the operation, before the operation is complete, and after the traffic has been restored to the device. And with all of this, we've been able to build a change management system which scales for the operations at Meta today. Putting it all together, we have built a scheduler and an orchestrator. We initially started with a problem statement on safely scheduling operations and shifting the traffic before and after the operation. Later, we supported the fleet-wide upgrades through the orchestrator. Then we added Evaluator and defined the initial version of operational policy for providing early warning system for the risk on the network. Later, we supported intent-aware scheduling to onboard 99% of the operations onto our network. And then we added the workflow-specific health checks. The impact of all of this has been tremendous. More than 1 million network operations happen on a yearly basis without major incidents on the network. Less than 0.5% human involvement is involved with all of these million changes on the network. We have up-to-date fleet with latest image and configurations, and we have an optimized repair resulting in lower MTTR. This journey is only 1% complete. The simpler abstractions around operations no longer work for large-scale migrations. We need to support newer abstractions. Even 0.5% human involvement is too high. We need newer ways to reduce the complexity on the network. And finally, explainability of our scheduler is a major challenge. These are all some things maybe we could present in the sequel of this talk in future nanogs. And takeaways, as I mentioned here, like backbone change management was not built on day one. It was an iterative process, which was improved through continuous work and partner feedback. And last not the least, metrics are extremely essential for identifying the system gaps and driving improvements. Thank you. Questions? Oh, hi.
Yeah? Okay.
Yeah.
Thank you very much, Karthik. My name is Marco Sanz from the Geeks. Thank you very much for the insights. Is any of the components you mentioned, like the orchestrator, or available as open source?
That's a good question. No, we do not. But I thought about it. One of the reasons why I wanted to share it is that I haven't seen publicly shared information on how change management is done in different orgs. But a lot of these systems, individual components, as you see, it's not. I think it can be iteratively built, and the smaller components can be improved over time. But yeah, we haven't open sourced it.
Thank you very much.
Yeah.
Hi, Logan Blythe. I was wondering if you can talk about anything below this automation. Like, what are you building on top of, or what is are you all building Facebook on top of your wedge switches, or anything further beneath the covers you can talk about?
So these change management services, they run almost in their own containers in as a separate services, and they manage. Yeah, how the changes are actually performed is slightly decoupled from this. That we have other systems which actually we have drivers which are which kind of provide that hardware abstraction layer and make individual changes on the network. But that's not in this talk.
Okay.
Yeah.
Thank you.
Cool. Thank you for all the questions.